When we're trying to understand the ideas of quantum mechanical identical particles, much of our confusion comes from the fact that we call the entities we've been discussing particles. This is mostly what a philosopher would call an ontological problem. If you look up the word ontology in a dictionary, it will give you a definition something like the nature of being. The ontology of something is essentially all the attributes it can have. For example, I am a real person. You cannot see through me. Now, if I was a ghost, then you'd be able at least partly to see through me. Whether or not I'm partially transparent is an ontological distinction between me and a ghost. Of course, as I said, since I'm not a ghost, you cannot see through me. When we think of a particle in our ordinary classical world, we attach attributes to it like size, shape, charge, mass, position, velocity, discreteness, countability, and uniqueness. These attributes are the particle's ontology. When we think about a quantum mechanical particle, we have to delete or modify most of this ontology. We could save time if we did not use the word particle. Then we could avoid having to unlearn parts of the previous ontology. Maybe we should call these quantum mechanical entities something else. Perhaps we could make up a word like quarticle instead of particle, with a letter Q at the beginning instead of a letter P, for example. Then at least we would avoid the mistake of bringing along all of the ontology of our idea of a classical particle. Of course, we're not going to do that now because the term particle, even for our quantum mechanical entities, has been used for too long. But we should understand that it's a mistake to give a quantum mechanical particle all of the ontological attributes of a classical one. From our list of attributes of a classical particle, for a quantum mechanical particle, we're left with only a few, such as charge, mass, some intertwined version of position and velocity or momentum from the uncertainty principle, some kind of discreteness, and heavily modified notions of counting. There are fewer ontological problems if we consider levels of excitation of modes. Instead of 3 photons in mode A and 2 in mode B, we could say that mode A is in its third level of excitation and mode B is in its second level of excitation. Counting is then simple, as in the bank account analogy. It does not matter if we never introduce particles, as long as we have the rules constructed by quantum mechanics for manipulating states. And it doesn't matter what words we then use. Practically, particles are here to stay, though. We would find it disquieting, I think, to think of electrons as being merely excitation levels of modes rather than being particles. That's a psychological problem rather than a physical one, but the price we pay is a self-inflicted confusion about quantum mechanics. The good news is that if we accept the rules of quantum mechanics and apply them faithfully, all of these problems go away. So far, we've used the word identical and avoided the word indistinguishable because there's a difference between these two concepts. There are two ideas here that we should not confuse. We believe all electrons are identical. They do not have separate identities or names, just as $2 in a bank account do not have distinct identities or names. We might, however, regard two specific electrons as being practically distinguishable. If they're so far apart that their interaction is negligible, then we can regard them as distinguishable because there's no physical process by which they could be swapped over. This is like saying we have $1 in a bank account in, say, California, and another in a bank account in Hawaii, but for some reason there are no communications between the two banks. When there is no possibility of exchange, it makes no difference to any calculation whether we symmetrize the two-particle wave function into its correct two-identical particle form. We saw this in discussing exchange energy for two electrons whose wave functions do not overlap. In this case, we can get away with treating these two distinguishable electrons as if they were non-identical particles. Because it will make no difference to this calculation, we can still symmetrize the wave function properly if we want to, however.
So, even if two particles are identical, if there is no reasonable physical process by which they could be swapped, such distinguishable particles can be treated as if they were non-identical.
It's also true that all photons are identical, just as all electrons are identical. This leads to the quite correct conclusion that a microwave photon and a gamma ray photon are identical. Photons in different modes, such as photons of different frequencies or photons going in different directions, mostly do not interact with one another, however. We can pass two light beams right through one another, for example. We can therefore often regard photons in different modes as being distinguishable, treating them as if they were non-identical particles, and hence dropping the symmetrization of the state in such cases. We cannot, however, always do that. If in doubt, we should symmetrize the state because that is always correct.
So, we can say as an approximation that two identical particles are distinguishable if the exchange interaction between them is negligibly small. Then the distinguishability lets us treat them as non-identical particles for practical purposes. Conversely, if we say that two particles are indistinguishable because of the possibility of exchange of them, then we are saying that we have to symmetrize the state properly with respect to exchange.